headfirst into one of those physics ideas that just feels wrong, you know? We're asking, why don't everyday objects, things you can actually see and touch, like your coffee cup or a baseball, why they act like waves?
Right. They seem so solid, so predictable.
Exactly. But then quantum mechanics comes along and insists everything, absolutely everything, has a wave nature.
It's a pretty fundamental concept, really. It comes from Louis de Broglie's groundbreaking work way back. He basically said wave-particle duality isn't just for light.
Not just photons and electrons.
Nope. It's universal. Every single particle, no matter how big or small, should have a wavelength associated with it.
Okay, but that just sounds wild when you think about, like, a bowling ball.
Yeah.
So we've got this fantastic source document here. It's called Quantum Waves and Macroscopic Reality, and it tackles this exact question.
It really gets into the weeds on this one.
Yeah. So our mission for this deep dive is to use this doc to, really unpack the science behind this apparent paradox. Why does our familiar world seem so classical?
It's like peeling back a layer, isn't it? Finding the quantum reality underneath.
Okay, so where does the document start? De Broglie.
Right. The first critical insight really comes from looking at de Broglie's equation itself. It's surprisingly simple.
Simple but powerful.
Very. It's just wavelength equals Planck's constant divided by momentum.
And momentum is just mass times velocity, right?
Exactly. P equals mv.
Okay, let's put some numbers on this. Planck's constant h. That's the key player here, isn't it? It's tiny.
Incredibly tiny, like almost unimaginably small. It's about 6.626 times 10 to the power of minus 34 joule seconds.
Minus 34, wow.
Yeah. So now let's plug that tiny number into the equation for something, every day, like a bowling ball, say 1 kilogram, rolling pretty slowly, maybe 1 meter per second.
Okay, easy math. Momentum is just 1 kilogram times 1 meters.
Yeah.
So?
Right, just 1. Now divide Planck's constant, that 10 to the minus 34 number, by 1. The de Broglie wavelength for that bowling ball comes out to 6.626 times 10 to the power of minus 34 meters.
Wait, hold on. 10 to the minus 34. That's not just small. That's ridiculously small.
It's staggeringly small. Let's try something lighter, a little paperclip, maybe 1 gram. Drifting really slowly, say 1/10 of a meter per second.
Okay.
Its wavelength is still around 6.626 times 10 to the power of minus 30 meters.
Minus 30. Still tiny.
Even tinier stuff, like a speck of dust. A microgram, moving slowly. Its wavelength is maybe near 6.626 times 10 to the power of minus 19 meters.
Okay, let me get some perspective here. A proton, that's about 10 to the minus 15 meters across, right?
Yeah.
And an atom is roughly 10 to the minus 10.
Correct.
So even that dust speck's wavelength, it's way smaller than a single proton. And the bowling ball, forget about it. Its wavelength is just dwarfed by literally anything we can measure or even conceive of.
And that is the first really crucial takeaway from the document. The de Broglie wavelengths of macroscopic objects are just extraordinarily tiny compared to their actual physical size.
Compared to anything they might interact with.
Precisely. Wave-like effects, things like diffraction or interference, they only really show up, only become significant when the wavelength is sort of comparable to, or maybe even bigger than, the thing it's hitting or the slit it's going through.
Like we see with electrons. Right. We can shoot them through tiny gaps and see interference patterns because their wavelengths are, relevant at that scale.
Exactly that. But for our bowling ball, with its 10 to the minus 34 meter wavelength, there's just nothing in the universe small enough, no gap, no edge, that could possibly interact with it in a way that reveals that waviness.
The ball itself is just trillions and trillions of times bigger than its own wavelength.
Yeah. The quantum waviness, you could say, is just completely smeared out. It's totally unobservable at our scale.
Okay, so reason number 1, massive scale mismatch. The wavelength is just too small to matter. What about quantum uncertainty? Heisenberg.
Ah, yes, the uncertainty principle. Absolutely fundamental. Can't know position and momentum perfectly at the same time.
So doesn't that introduce some fuzziness?
It does, in principle. But again, for macroscopic objects, think about their mass. It's huge compared to the quantum scale.
Right.
So even if you knew its momentum very precisely, the inherent quantum uncertainty in its position predicted by Heisenberg is still incredibly, incredibly small, much smaller than any possible measurement we could make.
So the uncertainty is there, theoretically, but practically.
Yeah.
It's negligible for big things.
Exactly. It just doesn't impact our everyday experience of where that bowling ball is.
Okay. Tiny wavelength, negligible uncertainty. That makes sense for, one big quantum particle. But a bowling ball isn't one particle, right? It's trillions upon trillions of atoms.
Staggering number, yes.
So I've heard people sort of suggests that maybe the waves of all those individual atoms just cancel each other out or average out somehow. Does the document talk about that?
It does address that, and it leads to the second and maybe even more profound reason why we don't see macroscopic quantum effects. The idea of averaging is kind of intuitive, but the physics is a bit more subtle.
Okay.
That de Broglie wavelength we calculated, the 10 to the minus 34 one, that's for the motion of the entire object's center of mass.
Ah, the object as a whole.
Yes. If, and this is a huge if, you could somehow keep that entire bowling ball in a perfectly isolated quantum state, totally shielded from everything, then that wavelength would describe its overall wave-like motion.
That's the whole point, isn't it?
Yeah.
Macroscopic objects were never isolated. They can't be.
Precisely. That's the crux of it. A macroscopic object, like a bowling ball or even that paperclip, is this stupendously complex system. You're talking, what, 10 to the power of 23, 10 to the 25 atoms or more?
Yeah, Avogadro's number territory.
And these atoms aren't just sitting still. They're constantly jiggling, vibrating, colliding with each other. And crucially, they are relentlessly interacting with their environment.
You mean like air molecules bouncing off it?
Air molecules, photons of light hitting it from the room lights or the sun, thermal radiation being emitted and absorbed, even cosmic rays zipping through, constant bombardment,
Okay.
and this constant, unavoidable interaction with the environment. This is where the quantum weirdness gets suppressed. The document really emphasizes a concept called decoherence.
Decoherent. Okay, I've said that too.
Quantum states, especially the really weird ones, like being in a superposition, being in multiple places at once, or being entangled with another particle, they are incredibly delicate, fragile.
Right.
Any interaction with the environment, even a single air molecule bumping into it or a photon scattering off it, acts like a tiny little measurement of the object's state.
And a measurement. In quantum mechanics, that's the thing that forces a choice, right? It collapses the wave function.
That's the absolute key. For something as large and complex as a bowling ball, these environmental interactions, these measurements, are happening constantly. Trillions upon trillions of times every single second from all directions.
Wow. I'm stuck.
This incessant measurement effectively destroys the phase coherence. That's the synchronized, aligned, wave-like behavior across the whole object that you'd need to see large-scale quantum effects like interference.
So the environment is constantly sort of watching it, and that prevents it from acting like a wave.
In essence, yes. It rapidly forces the object into what looks like a classical state. It appears to have a definite position, a definite momentum at all times, simply because the environment is constantly checking where it is. It kills the possibility of maintaining that large-scale quantum superposition or wave behavior.
So it's less about the internal waves averaging out and more about the environment actively, almost forcing it to be classical by constantly interacting with it, constantly measuring it, like nonstop poking and prodding kills the quantum vibe.
That's a really good way to put it. The quantum coherence, the potential for the object as a whole to exhibit wave properties, gets completely washed out, suppressed by this relentless decoherence from the environment.
Okay, that's a big piece of the puzzle.
And there's another related point the document makes. Think about the properties we actually observe in macroscopic objects, things like pressure, temperature, solidity, viscosity.
Yeah, the stuff we measure and feel.
Are those fundamental properties of the individual atoms?
No, I guess not. An individual atom doesn't have a temperature or pressure in the same way a gas does.
Exactly. These are emergent properties.
Emergent properties.
Yes, properties that don't exist at the level of the individual components, but emerge from the collective statistical behavior of that huge number of constituent particles.
So it's about the crowd, not the individual.
Precisely. While each individual atom or molecule inside that bowling ball is still fundamentally governed by quantum mechanics, their sheer numbers and their constant interactions lead to these very predictable, stable bulk behaviors that we describe perfectly well using classical physics and thermodynamics.
So the macroscopic world we see, the macro perspective, it emerges from averaging over these massive populations of quantum particles.
That's the picture. It's a statistical outcome. You're not typically seeing the wave nature of the whole object because its coherence is destroyed. And the properties you do see are these classical emergent ones based on the average behavior of zillions of quantum parts.
So the classical world isn't like a totally separate set of rules. It's more like a description that works really, really well when you zoom out from the quantum level and look at huge numbers of interacting particles.
That's a fantastic way to summarize it. And this idea is actually formalized in physics. Niels Bohr talked about the correspondence principle. The document points to this as well.
The correspondence principle. Okay, what does that say?
It basically states that the predictions of quantum mechanics have to match or correspond to the predictions of classical physics in the limit where quantum effects become negligible.
Which is when?
For large systems, large energies, large numbers. Essentially, anytime Planck's constant h becomes tiny compared to the other quantities involved, like the object's momentum times its size, what physicists call the action.
And for our bowling ball, its mass, its momentum, its physical action is just enormous compared to that tiny little h. So the h divided by p in the de Broglie wavelength becomes vanishingly small.
Exactly. It approaches zero for all practical purposes. So the quantum effects, while they're still fundamentally there according to the underlying theory, they just become completely invisible, practically unobservable. Classical mechanics then becomes an incredibly accurate and useful approximation for describing how bowling balls roll and, how coffee cups just sit there.
Okay, I think I'm getting the picture now. So putting it all together, it's like a multi-pronged explanation. First, the de Broglie wavelength itself is just absurdly small for anything big.
Far too small to interact with anything in a way that reveals waviness.
Right.
Second, even if it wasn't, the constant interaction with the environment decoherence smashes any large-scale quantum coherence before it can ever manifest. The environment forces it to look classical.
Constantly measuring it into a definite state. Yep.
And third, the properties we actually perceive in the macroscopic world aren't usually the quantum properties of the whole object anyway. They're emergent properties that arise from the statistical behavior of countless tiny quantum parts.
Nicely summarized.
So the underlying quantum rules haven't gone away. They're still running the show deep down, but their weirdest effects are just hidden, suppressed, averaged out in a complex way at the scale we live in.
That's the modern understanding, yes. It's a really powerful concept when you think about it. How this familiar, predictable, classical world we navigate every single day actually arises from this deeply strange, counterintuitive quantum reality. Through these complex processes like decoherence and statistical averaging.
Yeah, it's not a simple switch, but an emergence.
It really does make you stop and think, doesn't it? Like, what other things, everyday phenomena that we just take completely for granted, might also be emergent properties? Things arising from deeper, maybe much less obvious principles operating just beneath the surface we see.
It's a fascinating question, something to ponder, maybe, next time you pick up. Well, you mentioned it earlier. A paperclip,